11.6 Areas of regular polygons. And once again, this little word pops right in here, but we need to remember that little word has a lot of meaning. If we're talking about regular polygons today, quick reminder, that means all my sides are equal. And that means all my angles are equal. And it is so important to know that what we do here in areas of regular polygons only applies to regular polygons. Nothing can be concave, everything has to be convex. All my sides are equal, all my angles are equal. If any of that changes, don't use the formulas, don't use the process we talk about here today. Okay, so keep in mind this is for regular polygons. So I have some vocab here. Super important, some of these, especially a couple in the middle, that we know them, that we understand them, and half of our job in this section is being able to find those as well. So the first one is center of a polygon. I'm going to admit, not a super big thing to know about. It's the center point in the center of my polygon. By the way, I'm looking at this pentagon right here. This is my polygon right now. It's regular, so all my sides are equal. All my interior angles are equal. So I have this center of my polygon. Now, from the center, I have two lines that are coming out, and that's what's going to be the most important as we start working with my regular polygons. The first one is the radius, and this is important, of a polygon. It doesn't say the radius of the circle, it says the radius of a polygon. It goes from the center of the polygon, so this center point we found before, to a vertex on the polygon. So I go here to this vertex. By the way, this is one radius. How many radii would I have inside of this pentagon? I could have 5 because I have to go to a vertex, so I can only go to 4 other vertices. So I can only have 4 radii of this particular polygon, this pentagon. So from the center of a polygon to the vertex is the radius. I do want to state for you, and this is why this circle is drawn around my pentagon as well. You'll notice that the radius of my polygon is the same radius of the circle that's circumscribed around my polygon. So that radius still is shared with the circle, but this is the radius of the polygon that we're talking about. Okay, my next one. Let you copy that definition down for a minute. The perpendicular distance from the center of a polygon to the side of the polygon. And we know from way back in chapter 3 that if we go from a point to a line, the shortest distance is always perpendicular. So this is the shortest distance from the center to the edge of the polygon. Okay? And it's a perpendicular distance from the center to the side. So we have this A word here. Now, I love being in class and saying, how do you think you pronounce this? Okay? Because I get all kinds of different things. So the trick is, the word is apothem. And as I like to tell people, think of that little animal that scurries across the road, fakes being dead sometimes. And just for those of you that didn't know, that word is opossum. It starts with an O, though most people just call them possums. It starts with an O. But think about that you're saying opossum, but you have a lisp. It's a little bit hard to get the word out. So instead you get apothem. Okay? So it's the apothem of a polygon. And that's this perpendicular distance. So I'm going to do my best to always label it A. And try to make it so you can read my writing. How's that sound? All right, so this is apothem. Then we have the central angle of a regular polygon. So I'm going to change colors here one more time. I'm going to kind of draw it away from the other two things. The central angle of a regular polygon is the angle formed by 2 radii drawn to consecutive vertices. So if I start at my center here, and I go to one vertice for one radius, and I go to another vertice for the other radius, this is an angle here. And that's my central angle. Okay, so that one right down there, that's my central angle. Now, if you think about a pentagon, how many central angles could I draw? So I'm going to just try to draw it away here for a little bit so you can kind of see. So if I draw one to each one, I have 1 here, 2, 3, 4, and then a 5th one here. So I can actually draw it 5 times, 5 central angles. They'll all be identical because of everything being regular. So when we find our central angle, we're going to take 360 and divide by how many sides we have. Because every time in those regular polygons, we will have exactly the same number of central angles as we will sides of the polygon. This angle is going to be super important as we work to find the area, so we want to talk about that central angle. We want to be able to find it, okay? All right, so let's move on. You'll notice on the side here I have the chart for all the names of my polygons again. This is just a quick reminder, so if I tell you you have an octagon, you remember, oh yeah, 8 sides. I think this chart is throughout our notes 2, 3, 4, 5 times. But this is vocab you should know, so if you don't, here's a good reference to come back and check on it if you're not sure. All right, so in example 1, we're going to just talk about these angles, starting with our central angle. So in this diagram, ABCDEF is a regular hexagon. Okay, so we're going to start right away with our regular hexagon, meaning we have 6 sides, all of them are the same, and we're going to work on finding our angle measures. So the first one I want to look for is EGF. So if I start here to E, I go to G, that's a radius. I go to F, that's another radius. So this angle right here with 2 radiuses, this is a central angle. Okay, so just like we said above, we do 360 divided by how many sides there are. In this case, on a hexagon, there are 6 of them. So 360 divided by 6, that angle I'm talking about right now is 60 degrees. So this full angle in here is 60 degrees. All right, changing color so maybe it'll stand out a little bit. Now we're going to go to EGH. So EG is still my radius, but now G to H is my apothem, and I'm finding the angle here. So if you think about that apothem, it came down right into the center point, right, and cut that right in half. So it's going to cut my angle in half. So this is going to be half of my central angle. And half of my central angle, or 60 divided by 2, is going to be 30 degrees. We're going to just cut that 60 right in half to get that 30. Okay, I'm going to kind of blow up that triangle a little bit so you can kind of see it so far. We just found this 30 degrees right here. It was already 90 down here when we dropped that line down. All right, our last and final angle they want us to find is HEG. H was down here, E's here, G's here. So we're actually coming over here, we're actually finding this angle. Well, I see it's a right triangle. I have a 30-degree angle. What's that leave for the last angle? Looks like one of my specialty, right? A 30, 60, 90. So this one's going to be 30, 60, 90. Which reminds me, if I get a 30, 60, 90, a special triangle, I better follow all my special triangle rules from way back in Chapter 7. Don't happen to see anywhere in this chapter. Any way you see it, I'm going to have the short side across from the 30, doubled side across from the 90, and my short side times radical 3 across from the 60. So don't forget that rule because it will come back, and we will use it anytime we see a hexagon on these regular polygons. All right, page 2. You can already see lots of margin notes. I've got lots of information for you here. Okay, so we're working on area of this regular polygon. And you'll notice right away here they drew another hexagon. This is going to be a generic formula that will work for all triangles, or I'm sorry, for all regular polygons, but we're going to focus right now on just this one. One thing I wanted to show you as you look at this hexagon is it's a hexagon, but it looks like they cut it into pie pieces. There's exactly 6 of them, okay? And each of these pie pieces is a nice, perfect triangle. Okay, so let's think about a triangle. A triangle, usually to find the area, we need its base, we need its height, right? And the area would be 1/2 base times height. Okay, so the base here is the side of the hexagon. Its height, oh wait, that goes from the center perpendicular. Well, that would be the same thing as the apothem, right? So if I took 1/2, I took the side of the hexagon, and then I took the apothem, I could find the area of one of those triangles. And what's really nice is all the triangles are identical. So if I could do that one time, I could multiply it by 6, and I could find all of them. and it would find all my area all at once. That's a pretty nice thing. Okay, so just a quick reminder, this 6 times the sides, so there's 6 sides, 1, 2, 3, 4, 5, 6. Obviously on a different polygon, that number would be different. But do you notice that if I go around, this 6 times the sides is the same thing as the perimeter? So no matter how many, if it's a octagon, I do 8 sides. If it was a dodecagon, I do 12 sides. If I just think of whatever this number is, because it could change times the sides, it's always the perimeter. I have that 1/2, and then I have the apothem. Right there's my formula. That is the formula I'm going to use. It's 1/2 apothem times perimeter. That is the area for all regular polygons. So everything I showed you here with all these triangles, we're not going to have to worry about it. We need to find 2 things every time, the apothem length and the perimeter of the polygon, and that will find for us, used together, the area of the entire polygon. Okay, green formula sheet, I would write it down, and so when I write it down, my green formula sheet, this is found in 10, we're in chapter 11, what am I talking about? This is 11.6, and we're finding, and you could just write down regular polygon, because I wouldn't want to draw it because there's so many of them, right? We wouldn't want somebody to pick up the formula sheet and say, oh, this only works for hexagon. Nope, it works for any of them. So the area of a regular polygon equals 1/2 apothem times perimeter. You know what? Let's do a second thing. You might want to write out the word apothem, and you might want to draw a little arrow and say that this is the perimeter. And make sure we realize that's the perimeter of the polygon, not the triangle, of the polygon. Perimeter of polygon. Okay? So that should go on your formula sheet. It's nice and easy and going to be handy to be able to find that right there. Okay? All right, here we go. We have our first example here, and I have this huge list of notes in my margin. Okay, if you can follow this list of notes, you can find the area of any regular polygon. So it seems pretty straightforward to start with. I only need 2 things, the apothem and the perimeter. Sometimes, depending on how the information is given, we have more work than on some than we do on others. Okay, so a couple things here. I have this list, and I want to make sure you notice at the bottom of your page here how I have this little right triangle, okay? This right triangle is going to be the key to everything. As we work through these problems, you're going to see me draw this right triangle over and over and over. And the key is, can you label this right triangle? If you can fill in all the information on it, you will be able to find your perimeter and your apothem every time. So we go to our, let me change colors here so it sticks out maybe a little bit more. We go to our regular polygon. This regular polygon is a regular octagon, so we have an octagon right now. And the first thing we want to do is find the central angle of the polygon. So every time it's just 360 divided by n. And you're going to see this number all over. If you look at my answer keys, if you look at my work, you're always going to see me write 360 divided by how many sides there are. So in this particular one, I have 360. I'm going to divide it by 8 since there are 8 sides, and 360 divided by 8 is 45 degrees. So it's so important to realize that if I draw this little triangle right here that uses the side and uses 2 radii, that this angle inside right there is 45 degrees. And no matter what information they give you, as long as you know the sides of the triangle, or the sides of the polygon, you'll always be able to find your central angle. Okay, now I need to draw my apothem down. Okay, so I draw my triangle in the polygon, place the central angle at the top, radii at the side, so I did step 2. I'm going to drop the altitude in the triangle, which is my apothem, so I'm going to drop this straight down. Okay, I drop it right there. That's my apothem. Okay, so I'm going to be honest, I like to draw the half triangle, so I'm only going to focus here on this half triangle. So here it is. Okay, that's what I'm looking for. Well, careful. If I drop that apothem down, I now cut my central angle in half because I only care about half of that triangle, which is now a right triangle. I need half of my central angle, so that's 22.5. When I divide that 45 in half, I have a 22.5. Notice down here, what's at the top every time? Half my central angle. All right, my apothem is over here on the left. Over here on the right is my radius. And down on the bottom, if you think about it, this was my full side. This measure right here is half my side. Okay, so from here to here is just half of the side. Well, they told us that the side is 3 centimeters. That's my side there, so half of that is 1.5. So we do know that, okay? We need to know, and by the way, if my sides are 3, if I know I have half, the full side is 3. How many sides are on an octagon? There's 8. So if I do 8 times 3, I get 24 for my perimeter. By the way, that means half of my work's done because my perimeter's found. I need one more value, and that's my apothem. Okay? Now, on this one, they also gave me my radius, which I did a good job covering up there when I drew that. Let's see if I erase just a little bit. 3.92. Okay, let me. So this radius right now is 3.92. Quick heads up. Sometimes we need that radius to figure out other things. When it comes to my formula for area, I don't need the radius. I do use it to find other things. So right now, I have my right triangle. I have a central angle at the top of half a central angle of 22.5, a radius of 3.92, half a side of 1.5. I need the apothem yet. So multiple ways we can do this. My guess is most of you see a right triangle with 2 sides and say, let's use Pythagorean Theorem. So let's use Pythagorean Theorem. A squared plus B squared equals C squared. The most important one we have to place is C. That's across from my right angle. What is my C? That will be my 3.92. 1.5 into one spot, and I'm missing my other one. I'm going to call it my A for my apothem. All right, some math to do here. Calculator would be super handy here. By the way, I don't like how the book set this up. So 1.5 squared, that's about 2.25, plus my A squared equals 3.92 squared. Oh, it's a long one. You want to round it to about 15.4. Subtract that 2.25. A squared equals about 13.1. Again, I'm doing a little rounding here. Take the square root, and A comes out close to 3.6. Okay, most of the time, I'm going to tell you honestly, you're going to have decimals and you're going to round to the nearest 10, okay? When you should have simplified radicals, I'll tell you. I'll give you that hint. We'll kind of go over it before we end these notes today when you'll have that. All right, here's the nice thing, guys. We just found our apothem. We already know our perimeter. We have enough information right now to finish out and find the area of this coaster, this octagon, okay? So let's finish our formula here. Area equals 1/2 apothem times perimeter. So we have 1/2. We plug in our apothem of 3.6. We plug in our perimeter of 24. And remember, what this is doing is taking all those triangles. There were 8 of them in this octagon. It's finding all their areas together at the exact same time, since they all had the exact same base and they all had the exact same altitude or apothem. And we get an area when we run these numbers through of about 43.2. And that will be centimeters squared because it's area. Okay. By the way, we dropped that altitude down the apothem. We labeled the angles and sides we knew. We found the missing piece, which in this case was the apothem. That's what we needed. And we plugged the numbers into the area formula. Okay, I can't stress enough this little triangle. This is going to be the key to everything we do here. When I look for work on your papers, I'm going to look for this triangle every time. Because if you can properly label this triangle, you can do every one of these type of problems. Okay, let's turn the page and try some more. First example up here, we're going to work on just angles again. This one is a square, and we're going to find angle FKJ. That's a central angle. So my measure of angle FKJ, which I'm going to put just a reminder to myself, it's a central angle. So if it's a central angle, I'm going to do 360 divided by how many sides? Well, how many sides are on a square? 4. So it looks like I get 90 degrees for my central angle. My second one is KJF. And I'm going to change colors here so we can see this. KJF. KJF, this angle right here. Okay, so let's do a little work here. I had 90 at the top, and when I drop my apothem down, it splits it in half. So half of 90 is 45. So this top angle is 45. So I'm looking for this bottom angle. Well, we know that if we have a 90 and a 45, that leaves me another 45. So it looks like this angle is going to be 45 degrees. Okay. Remember the advantage of doing that apothem every time, we always end up with a right triangle, so we can go back to either our special right triangles or our trig to be able to find things on those. Okay. Number 2, the radius of the regular pentagon here is 6.8, and I want to find the area to the nearest square inch. I will tell you every time I do these problems, and I do this on your homework, I find it best to break my problem down into 2 things. I need to find my perimeter, and then I need to find my apothem. So if I know that my regular pentagon here has a side value of 8, which I do believe they give it to me, right? Yeah, they do. So my perimeter, there's 5 sides on my pentagon, 8 inches, and I get a perimeter of 40. Okay. This is half of the work I need for my area to plug in. So now I need to work on my apothem. I'm going to be honest, guys, I always shortcut and go straight to the half triangle, okay? I will do 360 divided by 5. 360 divided by 5 is 72. So when I go to label this triangle, I always put half of that. So what's half of 72? 36. So I get a 36-degree angle at the top. They gave me the radius over here is 6.8, so I can label the radius. And I'm looking for my apothem. This is the information they give me. They did give me the side was 8, and so my half side is 4. Knowing this, I can go ahead and do a little Pythagorean Theorem, right? A squared plus b squared equals c squared. Which one has to be my c? Well, across from my right angle has to be my c, so that's going to be 6.8. I'm going to let my apothem stay a, and b will be 4. So a squared plus 16, 6.8 squared. Calculator, we're at 46.24. Subtract that 16, and get 30.24. Take the square root, and my apothem is about, what do you say, 5.5-ish when we round that? All right, 2 important things, my perimeter and my apothem. I have them both. I'm ready to find my area. Area equals 1/2 apothem times perimeter. 1/2, my apothem is 5.5. My perimeter is 40. And I run that together. Nothing is exact because I already rounded on my apothem. So it looks like I get about 110 inches squared because I am working with area. Okay. All right, let's try another one. Okay. You're going to notice as we go on that sometimes we get less and less information. And that's important to know and important to realize that we have the tools, however, to find it. So they really don't have to give us very much information to be able to solve one of these. All right, our next one here, we're working with a nonagon. How many sides on a nonagon? 9. It's important to know this. So first things first, 9 sides, 360 divided by 9 gives me a central angle of 40 degrees. Okay, so we're working with this 40 degrees. Let's go ahead and I'm going to draw this triangle. This is going to be the key to everything I do is my half triangle. Okay, they keep drawing this full thing over here. I think it's easier to go straight to the half. Once I know my central angle, I'm going to take half of it and I'm going to put my top angle there is 20. Always half of that. Okay, you'll notice on my nonagon they gave me one piece of information. They gave me my radius of 5. That's all they gave me. Radius always is my hypotenuse, so there's my 5 right there. It's always on the hypotenuse. It's a great number, but I need to have my apothem, and I need to have my half side down here to be able to find my perimeter. Notice this is the first time they didn't give me anything about my sides, so I could find my perimeter so easy. I've got some work to do. Okay, so my apothem's over here. I'm going to call it X. My half side's down here. I'm going to call it Y. Do I have enough information to be able to find them? I do. Because I know from chapter 7 that if I have a right triangle, one side, I can find anything I need. I'm going to start with side A here. It is the closest to my angle. It is adjacent, right? And I already know my 5, which is my hypotenuse. So let's think back to chapter 7. How about a little so, ka, toa? If I want to work with my adjacent and my hypotenuse, I'm doing a little ka work. Okay, so I'm going to set up the cosine of 20 degrees, that's my angle, equals the adjacent, which is x, over my hypotenuse, which is 5. Notice in everything I plugged in, I'm missing one thing, and that looks like the x. So how do I get x by itself? Multiply both sides by 5. This side cancels. 5 times cosine 20 equals x. Make sure your calculator's in degree mode, and go ahead and hit 5 times the cosine of 20 degrees. As long as you're in degree mode, you should be good. We'll run that through your calculator. What do we get? My calculator's telling me about 4.7. So this apothem over here is about 4.7. That's going to be, wow, can't even write the right number I just said. 4.7. And that's important because that is going to be on my apothem. I am going to use that in my formula. Okay, let's work now on this half side. And this is one that takes a little more getting used to, and we have to think about what we have and what we get. So now I'm going to work on the half side from my angle that is opposite. And once again, I like to use the number they start me with, so I'm going to use my hypotenuse again. So if I'm working with opposite and hypotenuse, I'm doing a little so work. Okay. I'm going to be honest, guys. They had it set up for me over here. I'm going to use this space. The sine of 20 degrees equals opposite, which is y, over 5, which is my hypotenuse. Once again, I need to get my variable by itself. Right now, there's a 5 connected to my y. It's connected by division. How do I get rid of division? I multiply. So I multiply by 5. What I do to one side, I have to do to the other one. So I'm going to type in 5 times the sine of 20 this time. Looks so close to what we did before, but this time it's the sine. It's going to give me a different answer. So again, make sure your calculator's in degree mode. Hit 5 times the sine of 20. And I should get about 1.7. Okay, so that's my half side. Okay, so let's walk through this. My half side is 1.7. So my full side is going to be 2 times 1.7. Okay, that's what I need for my full side. So one side is 3.4. So this is a side. Okay, how many sides are there on my nonagon? There's 9 sides. So 9 sides times my 3.4 will give me a perimeter of, what do we have? 30.8. Doesn't even sound right. Okay. 6, 3, 27, 22, 30.6. How about 30.6 there for my perimeter? By the way, if you leave numbers in your calculator, so let's say you had that 1.7 in there. I rounded it obviously to write it down on my paper, but if you just have it in your calculator and then you hit times 2 to get your full side and then you hit times 9, that's where my 30.8 came from earlier I had written down. But if you are rounding to 1.7, then times 2 is 3.4 times 9. If you're always ending your rounding, you might have a slightly different perimeter or a number when you get done than somebody else. That's okay. Don't worry about it. Okay? It's fine if you have that different. Okay, super important to realize we've got the hard work done. We're ready to finalize this, okay? So we have 1/2. We need the apothem. We have that over here, 4.7. We need the perimeter. We just found that, 30.6. And we're going to run that through our calculator. It's all multiplication. So 1/2 times 4.7 times 30.6. I have about 71.9 square units, okay? How are we feeling on this? That was a lot of work to get to that. When we only need an apothem and a perimeter, it took us a while to get there. But we have the skills because we have our trig from chapter 7, so we are able to do that when they give us one piece of information. All right, let's go to page 4. If it makes you feel better, there's not that much work on page 4 here. Okay, margin note here. I cannot stress enough. Give simplified radical answers, and these are the 3 shapes. Now, I'm going to be honest, I'm nice to you on your homework. Every time there should be a simplified radical answer, I tell you that in the directions, so you'll be able to see that. But I'm going to need simplified radical answers for equilateral triangles, and let me give you a heads up why. When I draw my half triangle in an equilateral triangle, 360 divided by 3 is 120. Half of that is 60. I get a 30, 60, 90. Okay? On a square, we'll keep them green, I guess. I draw my triangle. I do 360 divided by 4. I get 90. Half of that, 45. I get a 45, 45, 90 triangle. Hexagons. To find my central angle, 360 divided by 6, I get 60. Half of that is 30. I get another 30, 60, 90. If you get equilateral triangles, squares, or hexagons, you need to give simplified radical answers. Do not give decimals, okay? So that's just kind of a heads up. And again, I'll try to lead you through that when I give you those. But if I forget to, kind of think back to this rule. This is when I want those answers. Okay, so let's go ahead and do this problem here. I want the perimeter and then the area of this equilateral triangle inscribed in circle F. Okay. First things first, central angle, 360. It is a triangle, right? So I divide by 3 and I get 120. Draw my triangle. I want half of that. So I get this top angle of 60, always my right triangle. That means I have 30 down here. All right, they gave me one number. If you notice this, it goes from the center to the vertex. That's called our radius. That's going to be my hypotenuse there. That's my radius. Okay, I have a 30, 60, 90. Did they give me the short, the doubled, or the radical 3 side? Well, my short's across from my 30. It's missing. Across from my 90 is my doubled, and that's a 6. So if my doubled is a 6, what's my short? It'd be 3. So across from my 30 is going to go 3. And across from my 90 is the doubled, which is 6. And across from the 60 is always my short times radical 3. Now, wasn't that a little bit faster to fill in than our last one where we had to do all of our SOHCAHTOA? You might actually appreciate your special triangles a little more here. Okay, so remember, on my triangle here that I always draw, this bottom part right here is my half side. If my half side is 3 radical 3, my full side should be double that. So I'm going to take 2 times 3 radical 3. So my full side is 6 radical 3. How many sides are on a triangle? Well, there's 3 sides. Of 6 radical 3, that means I get 18 radical 3 for my perimeter. All right, we did half of it. We found the perimeter. We need an apothem. We already have it. There's my apothem already. We labeled it earlier as our short side. We have the 2 pieces of information we need. We're ready to find our area. Area equals 1/2 apothem times perimeter. So my apothem is 3, and my perimeter is 18 radical 3. All right, quick reminder, because I want to leave this answer in simplified radical. I get to use this 1/2 once. Do you want to use the 1/2 on the 3 or the 1/2 on the 18? Personally, I like 1/2 on 18. Half of 18 is 9. 9 times 3 is 27. And that radical 3 just gets to hang out. It doesn't really go anywhere. And my area is not. You might start to appreciate those special triangles. That's my thinking anyways. Okay. So, this bottom chart, it's not anything we need to go through. It's just kind of a reminder that as you find these triangles as you find information in your regular polygon. What tools do we have from earlier notes that you can do? So things we can use. Pythagorean Theorem, when you're missing one side of your right triangle. Special right triangles, your 30, 60, 90s, your 45, 45, 90s, something like that. So think about that. And then your trig, your SOHCAHTOA, okay? Those are things you can use to be able to go there. By the way, we did a 30, 60, 90 earlier. I'm going to do one more of them so you can see it. Okay, 30, 60, 90, short, doubled, radical 3s across from the 60. Don't forget on your 45, 45, 90, and you can find these on your Chapter 7 gold notes. Remember, these two are the same, and then you get x radical 2 as your hypotenuse, okay? But that's the things we're going to use there. So you have homework, okay, a worksheet. I can't stress enough, you really, really, really need to practice this. This is the toughest section in Chapter 11, okay? I actually have 2 more pages of notes. I'm going to do it this way, though. I'm going to stop the notes right now, and then I'm going to do those 2 pages separately. So if you want to go back and just watch examples of doing problem after problem after problem, it'll be a separate video, and you don't have to rewatch all of this one. Okay, so this was the basic notes. I'm going to stop it, and I'm going to do the extra examples on a separate video.